Convolution is a very basic theorem to be remembered in electrical engineering when you solve problems in frequency domain. The convolution is a process to find out the output from the input and the characteristics of a system. So basically, when you input certain signal to a particular system, you are bound to get some output. And there are ways to calculate this output mathematically. And this mathematical process is called as convolution. The output is the convolution of these two functions. So basically, one of the functions is the input mathematical function, and the other function is the characteristic equation or the transfer function of the system. So after convoluting these two signals together, you get the output. Convolution is nothing but revolving one signal with another. You can call it mixing in simple language. And this mixing is done mathematically, and hence integration is used while we solve convolution in time domain. But this very convolution, however it seems difficult while we solve it in the time domain, is very simple when we convert it into the Laplace transform, that means frequency domain. Let us see convolution in detail. So basically, as I described, you have x of t as an input here, f of t here is the system characteristic, and y of t is your output. Now you are going to get y of t as an output when you convolve x of t and f of t. And what is the formula for this convolution? It is y of t is equal to x of t convolution f of t. It's given by integration 0 to t f of t minus tau into x of tau d tau. Remember, the variable here is tau. Alright, and you are getting the output in t, because when you solve this particular integral, your all taus are going to be replaced by this t. Alright, so this is a complicated integration that you need to perform to get the value of y of t. Alright, so there must be some simple method, and this is where Laplace transform is very useful, because in Laplace transform, if you simply convert each signal's mathematical equation into the respective Laplace transform, f of t converts into f of s, and y of t will be y of s, then y of s is given as x of s multiplied by f of s. So basically this complicated convolution just converts into multiplication. Alright, and what is the proof behind this? We can prove it? Yes, of course we can. Using the basic definition of Laplace transform and using this integration, we can prove that this convolution is converted as the multiplication in frequency domain. Let me just quickly show you an example. So if x of t is e raised to minus t, and if f of t is e raised to minus 2t, alright, your output will be convolution of e raised to minus t and e raised to minus 2t. Okay, now you cannot simply convolve this using this particular equation, or I'm not going to put my time solving this complicated integration. Instead, what I'll do is I'll take the Laplace transform of this, which will be 1 upon 1 plus s, and multiply it with the Laplace transform of this particular function, 2 plus s. Okay, so what is the output? It will be 1 upon s plus 1 and s plus 2. If I convert this into partial fractions, let me assume a upon s plus 1 plus b upon s plus 2. If I solve this, I get a and b's values. A is equal to plus 1 and b is equal to minus 1. So while you get these values, your output will be 1 upon s plus 1 minus 1 upon s plus 2. And now you can take the inverse Laplace of each function. So you will have e raised to minus t minus e raised to minus 2t. So this is nothing but the output y of t. So I have bypassed whole difficult situation when I had to solve this particular integration, and still I arrived at my output y of t by using the Laplace transform. So basically when you have input e raised to minus t and system transfer function is e raised to minus 2t, you will get e raised to minus t minus e raised to minus 2t as your output. Let us see the proof of this particular theorem. So you are taking Laplace transform of convolution of x of t and f of t. According to definition, inside the square bracket, you are seeing the convolution integral from tau equal to 0 to t, x of t minus tau into f of tau d tau. Outside of the bracket, we are multiplying according to Laplace transform's definition, e raised to minus st into dt. Now what we are going to do is, we are going to multiply the function inside by u of t minus tau. Alright, as you can see this function, if this is my time graph, this will be my tau. Alright, so for t less than tau, the function is going to return the value 0 anyway. That means for tau greater than t, it will be 0. So I just reversed the values. So basically this tau is varying from 0 to t. I don't want the values for tau after t. So I can just multiply this function by u of t minus tau and change the limits from tau equal to 0 to infinity, because it will not change the overall impression of the function inside. As this particular tau goes beyond t, it will return value 0 anyway. So I am just changing the limits over here. Okay. And we have multiplied by u of t minus tau. Now, as we have the limits which do not have any variable now, we can change this d tau as is equal to dt, right? Because they are interchangeable. So I am bringing in this dt inside and d tau will be taken outside. Okay. Now we have dt inside, and because dt is inside, f of tau will not be function of t. Alright. So f of tau is taken outside. Inside we have x of t minus tau and u of t minus tau. This is nothing but x of t, u of t shifted by tau. So we are multiplying it by e raised to minus s tau. Okay. So this is the function inside. And this e raised to minus s tau is replaced by e raised to minus st, so that we get x of t, u of t, and e raised to minus st dt. Now if you can see, this is nothing but the Laplace transform of x of t, because the limits are 0 to infinity. So this is going to return value 1, and we can change this as x of s, right? So inner integral, it is x of s now, and outside we have f of tau e raised to minus s tau. Alright, because we had replaced it. Because we have the limits which do not have any variable, we have changed the dt from d tau. Okay, so anyway we had taken this out, so we can just assume this was d tau, so this remains same. And now we have x of s, which is constant, which is taken outside, and the remaining of the function you can see is f of s. So basically y of s is equal to x of s into f of s is true. I hope you have understood the use and the importance of convolution, and I also hope you have understood this proof. I will meet you again whenever you call me back. Thank you so much.